At the beginning of the 21st century, Dubai solved a problem no city had ever solved before.
The city was growing faster than its natural limits. Every square meter was being pushed harder than ever before. But the coastline was not. So engineers proposed something radical. What if the city didn't stop at the shore? What if it moved into the sea?
Behind me, nothing but open water. In 2001, this entire coastline looked exactly like this.
That idea sounded impossible at first. The ocean doesn't cooperate. Waves never stop. Sand never stays still.
This ground behaves almost like liquid under pressure. That makes building here extremely tricky. Before anything could be built, the ocean had to be controlled.
The first step was protection. Engineers designed a massive breakwater, a giant curved barrier made from millions of tons of rock. Its job was simple: absorb wave energy and create calm water behind it. Rock quarries across the UAE began blasting limestone. Huge blocks were cut, sorted, and transported to the coast. Specialized ships carried the stones offshore. Each block was dropped with precision, guided by GPS systems accurate to centimeters.
Okay, hold it there. Perfect.
Layer by layer, the barrier slowly rose above sea level.
These rocks are not random. Smaller stones absorb wave impact. Larger armor rocks break the force of incoming waves.
Without this barrier, everything inside would simply wash away. This wall doesn't stop the ocean, it tames it. As the barrier closed into its final shape, the water inside became calmer. Now, the real island could begin. Massive dredging ships moved into position. They vacuumed sand from the seabed, mixed it with water, and pumped it through kilometers of floating pipelines. At the nozzle, the sand sprayed into the air like a rainbow. That's where the process got its name, rainbowing. Millions of cubic meters of sand were sprayed into shape, slowly forming the palm's trunk, fronds, and crescent. From the air, it looked artistic, but on the ground, it was precise engineering. Every contour had elevation targets. Every slope had stability limits.
This pipe is moving thousands of tons of sand every hour. What looks like chaos is actually mapped down to exact coordinates. One section is too high or too low, water flow changes, and erosion starts. So everything has to be perfect.
But loose sand isn't strong enough to support buildings.
You can see the sidewall collapse, water bleeding at the surface, and a clear loss of load resistance.
Under heavy load, it shifts and settles. So engineers had to lock it in place. The solution was Vibro-Compaction. Long steel probes were driven deep into the sand. They vibrated at high frequency, forcing sand particles to rearrange and pack tightly together. Air and water were squeezed out. Density increased. Stability improved. What started as loose seabed became solid ground capable of supporting skyscrapers.
If this sand stayed loose, a building would slowly sink or tilt. Vibration forces the grains to lock together. You're basically turning liquid sand into rock-solid ground.
Each zone was tested repeatedly.
Engineers applied real construction loads to the ground. They measured how much the surface moved under pressure and confirmed it stayed within strict safety limits. That meant the land could now support heavy structures. To confirm the results, engineers extracted solid core samples. If the sand stayed loose, the sample would collapse. But this one held together.
You can see it holds its shape perfectly. That only happens when the ground is fully compacted.
Only after passing inspection could infrastructure begin. Before any buildings appeared, an entire underground city had to be installed. Power cables, water pipelines, sewage systems, telecommunication ducts, precision mapping guided every trench. Nothing could be misplaced. One wrong line could disrupt thousands of future residents. Road foundations followed.
All right, let's keep it moving. Looking good. Signal them.
Curbs, bridges,
Hold it there. Okay, bring it up.
access routes. The island was becoming functional before it became visible.
Most people never see this part. Everything that makes a city work has to go underground first. Once the buildings rise, you can't fix mistakes easily. So this phase has zero room for error.
With the ground stabilized and infrastructure ready, vertical construction began. Villas lined the fronds. Roads connected neighborhoods. Marinas filled with yachts. And at the crown of the palm, one massive structure rose: Atlantis, a landmark built directly on reclaimed land. Heavy foundations, complex load distribution, extreme precision. Every crane movement mattered. Every concrete pour was monitored. Every delivery synchronized.
This hotel alone weighs hundreds of thousands of tons. Building something this heavy on land that used to be water is pure engineering confidence.
Environmental monitoring never stopped. Water quality sensors tracked sediment flow. Marine life surveys monitored ecosystem health. Currents were analyzed constantly. Engineers adjusted designs in real time to minimize long-term impact. The island wasn't just built, it was balanced. What began as open sea became a fully functional extension of Dubai, a new coastline, new neighborhoods, new economic zones, built from sand, stone, planning, and patience.
Standing here today, it's hard to imagine this was ever empty water. Palm Jumeirah stands as proof that engineering can reshape geography itself. This was iTechX. Thanks for watching.